Okay, well, thank you very much. It's a real pleasure to be here, and I'm looking forward to learning more about what all of you are working on. I saw hints of some interesting poster titles, and hope to have a chance at lunch and other times to speak more with you about your ongoing work. So I was asked to give an overview about some of the current observations on disks to understand some of the initial conditions that might be impacting the demographics. That is the purpose of the workshop this week. So as an idea of where I thought it might be useful to head, I thought I would start off, since it's a demographic study, to have a little overview on some of the demographics that might be linked towards disk properties, and then to go on with just the basics, not knowing some of you may come from a strictly exoplanet observation or theory background, and so just an overview of star and planet formation and how observations are linked to those ideas. And then understand about how we know whether or not an object has a disk. What sort of lifetimes do those disks have? That's an important parameter for planet formation. And then understand how we go about interpreting the observations that are made of disks. And then how do those, thinking about demographics of disks as well, so what are the properties of disks in different regions around objects of different mass and objects of different evolutionary stages, and then another common type of star around binary systems. Okay, so we'll just start off with a brief overview of some of the demographics of exoplanets that might link back to disk properties. So we've seen earlier today this standard view of the exoplanet population shown up here in the graph on the right, where the y-axis is the mass and the x-axis is the separation here. And all these different colors are indicating, as was introduced previously, that these are all different techniques that have been applied to discover exoplanets, and so each of those have their own observational biases, and I think you'll be learning quite a bit more about those throughout the week. And so by focusing on a given technique, that can help us to tease out some of the demographics that are less impacted by these biases. So one example is to go ahead and take these green points are from radial velocity studies, and so if we investigate simply the radial velocity detections, then what we can find on this first plot on the left is an indication of the average planet mass as a function of the host star mass. And so going from lower mass objects on the left to higher mass objects on the right, you see that there's a possible scaling of the sort of average mass of a planet with the average mass of the host star. And then similarly here, there's the frequency of planets as a function of that host star mass, again limiting to radial velocity planets to help reduce those biases. And so this is giving us an indication that there are important trends with host object mass that then we can go back to the disk population and understand if we see similarly trends with object mass that we can possibly link with some of these demographics of the planet population. Okay, so another type of system that has been found to have exoplanet systems that might have originally been a bit of a surprise, but has made for some really spectacular artist renditions. So there are examples known of planets in binary systems, and so these come in different varieties. Here's an example. One of the first discovered exoplanets, around 16 Sig B, is a member of a very wide binary system. So in this case, one star hosts a planetary system and then one doesn't. And both have been searched with radial velocity, and I'm sure by a number of other techniques as well. And so that's one example where there's a planet around one of the stars, and then also these really intriguing Kepler discoveries where there are planets orbiting around the binary pair. And so it's important then to go and look at the disk population and understand, well, given that disks provide the reservoir material for planet formation, what are the properties then of disks in these type of systems? Like, for example, circumbinary disks, or disks around individual components of stars. Okay, and then another thing to keep in mind as we're looking forward at these workshops, it's always a really exciting time to be thinking about what's upcoming in the field. And there's an upcoming NASA mission that will provide, as was described in the previous talk, not necessarily a new slice of parameter space, but a very detailed study of nearby stars. So this is the TESS mission that will be investigating its target set are bright stars. And so if you look at the population of field stars nearby, so which are the targets of TESS? So this is disproportionately, the nearby stars will be weighted towards low mass stars. So these M stars will be a very large percentage of what will be investigated with TESS. And so it's important to understand then what are the properties of disks around these lower mass stars. And these have been more challenging until recently to be investigated in the same way that disks have been studied simply because of sensitivity limits. But now with breakthroughs with ALMA, it's possible to be pushing down to understand, while we can't go back in time and understand the disks around these nearby M stars, we can look to regions of much younger stars and study the disks around those low mass M stars. Okay, and then finally another technique that has its own observational biases. So thinking about directly imaged planets. So what's shown here is a little census, somewhat generously defined. It's just taken from the exoplanet.eu website. This is lining up all the host objects that have a planetary mass companion of sorts that are listed in this exoplanet database. And so they're shown as the separation increasing, and then the color indicates what type of host star object, depending on the mass. And so these targets are preferentially geared towards the youngest objects because that makes the planets more detectable. And so you can see examples where there are planets known in systems with debris disks, typically. And so this gives us an indication that we can learn from the disk something about the planet formation and the interactions of planets and disks. And if we look specifically at planetary mass objects that have been imaged around a particular young set of objects in the SCO-SEN association, this is now a region that's only in the sort of 5 to 10 million year old range. Then there are, we can investigate, well, for the systems that have planetary mass companions, what types of disks do they have? In some cases, they have interesting gaps that are modeled as individual, single gaps, possibly two gaps. And then in some cases, the companions themselves even have indications of disk material around them. And so this may give us information that we can use to understand, are the planets forming in the disk? Are they forming independently? And give us some indication of their starting point. Okay, so just a brief overview then of the star and planet formation process. This is sort of like a cartoon version. You'll hear much more detailed theoretical descriptions, and so I'll leave the detailed modeling to the theorist. I'm an observer, but this gives you an indication of the overall picture of a large cloud collapsing into clumps, condensing further, forming a disk around young star, and then ultimately planets forming out of that disk. And just so that you know that this cartoon is not strictly a cartoon, we have, in fact, observations of all of these stages. So what's shown over on this linear progression on the right up to here, I should have substituted one of those imaged exoplanets, for example. But what you see here is the progression in young stellar regions, and here is the area that we'll focus on. This is an image of a disk in a young star-forming region, and that dark lane you see is the dust in this disk, viewed more edge-on and obscuring the starlight behind the disk. So this gives you an example of where you can see in the optical an evidence of a disk and spatially resolve the structure, but that's not required to understand that a disk is present. You don't have to have this absolutely spectacular HST image to know that there is a disk. And so ways that we can go about understanding on a larger population sense if there are disks present around young stars and of what variety is to investigate what's called the spectral energy distribution. So this is showing the basically the power being emitted by the object as a function of wavelength. And so as you're going to longer and longer wavelengths at this earliest stage, that's the only indication you have of the object because it's so heavily embedded and obscured. But then going to later evolutionary phase where some of the material has cleared out. Then you see this dashed line is meant to be just the photosphere of the object itself, and then all of this excess emission above the photosphere is indicating that there's extra material present. And so this is, at this class 1 stage, the system is thought to have not only a disk, but also envelope material. By the class 2 stage, much of that envelope has been cleared away, and so really it's a stellar photosphere plus disk emission. And then by this class 3, you might have a really weak signature, and that's an object of intense scrutiny observationally to search for these weak debris disk excesses that then some of those systems have subsequently been imaged very nicely to see the structures of the disks themselves. So there's evidence both on the resolved imaging side that we really can connect objects that have spectral energy distributions of these shapes with actual physical structures of disks. Okay, so we can use those measurements to infer the presence of a disk to understand something about the disk frequencies and lifetimes. And those are really key properties for understanding how long do these theoretical mechanisms have to produce planets. Okay, so for understanding how we go about getting those observations to infer the presence of a disk, there are a wide variety of facilities. Many of you have probably used a number of these, but just as examples of some that have been involved in large surveys to investigate disk properties, there's Spitzer satellite that's still operating in the shortest wavelength regimes. There were large legacy surveys that have provided invaluable data sets for understanding disk census of many star-forming regions. More recently, there was the Herschel Space Observatory that targeted a number of these regions. And then something that I think all of you can be looking forward to is the ALMA observatory that has only just begun to start surveying regions. And what I'll show is really a pre-ALMA view of some of the statistics. And I think that will rapidly change as programs are executed with really whole regions in mind for surveys. Okay. So what we measure when we investigate these spectral energy distributions of young stars is each of those sort of facilities will cover a different wavelength regime. And even at the near IR or mid IR, it's possible to infer the presence of a disk. And so with a large-scale imaging map, then you can understand in a population sense how many of these objects have disks. And what's shown over on the right is an indication of where in the disk, so at what sort of distance from the central object, this emission is coming from. So with the shorter wavelengths quite close to the host object, and then on out to the submillimeter and millimeter, much farther from the star, or brown dwarf, whatever the case may be. And in some cases, even planetary mass objects. Okay, so by looking then at regions that have age estimates and spanning a range of ages across this critical timescale of several millions of years, so from the youngest regions of less than 1 million year out to associations that are on the order of 10 million years, we can track with these large-scale census programs the frequency of objects that have disks. And what we see is a very impressive decline over a very limited amount of lifetime for the presence of a disk. So that then gives an indication of how long it's possible. Now what's being measured is a dust emission excess, and then what is assumed is that that's linked as well to the presence of a gas disk that might be required, for example, to form giant planets. So that's the first indication of how the disk observations can impact our interpretation of planet formation models. Okay, and then there are certainly experts here who will be describing the latest details on these models, but generally they fall into two categories of models where either there's a buildup from small particles to ever larger cores that then capture an envelope through a core accretion process, or separately a gravitational instability model whereby the disk at an early phase has a rapid collapse to form a giant planet. And I think we'll have talks on both of those types of models later in the workshop. Okay, so then when we understand the spectral energy distribution, when we built that up with all our observations, what then can we infer from those observations just in some of the core properties that you can determine from disks about that? So this again shows the example of that spectral energy distribution here on the left, an indication of where the emission is coming from within the disk on the right. And then just one example of, there are a number of models out there. There's one example called MCFOS, that's a radiative transfer setup, where the photons from the central object are the starting point. And so given the effective temperature of the object, those photons are then sent out into a grid to solve a radiative transfer problem for a disk of a given structure. So there are structural parameters like the inner, outer disk, the scale height, the surface density profile, the grain properties, what sort of sizes and what distribution of those sizes are present in the disk, and then what sort of overall disk mass is there. And so those are the types of, now it's not, there's certainly degeneracies in these models, but that gives you an indication of the factors that go in. And I'll show you how some of the wavelength regions are appropriate to learning about different aspects of these disk structure parameters. So if we look at the far IR emission, and so the example here would be like in the Herschel data sets that are available. If we look at the structure, like the geometric structure of the disk that can impact the far IR emission, and what you see down here are two disks that are otherwise the same, but have different amounts of flaring. And so with different amounts of flaring, then you see this white zone, which is covering the far IR wavelengths. You'll have a different shape in the spectral energy distribution. So this gives you an idea of how, from even unresolved data, it's possible to learn about the disk properties. And then that can be factored in to starting points for planet simulations. Okay, another region of considerable interest is the even longer wavelength, so in the submillimeter and millimeter regime. At this point, the emission is approximated as being optically thin, and so then the flux that's measured can be directly related to the mass of the disk. And so what you see here in this example of several SEDs that have otherwise the same properties but different masses, what you see is that the flux in this, again, this white region is calling out the submillimeter and millimeter. You see how the flux is increasing as you have a larger and larger disk mass. Okay, and then another aspect that we can learn from this particular region is to understand the slope of that emission, and that links to the distribution of sizes of the dust particles. So we can infer evidence of grain growth, one of those key steps in the planet formation process, from observations at several wavelengths in this regime. Okay, so then let's go ahead and take a look at what sort of properties are seen for disks in different regions. And this is an area where I think our understanding will greatly improve as we have larger data sets coming in from ALMA approved programs. But this is sort of the current state of things. And so what's shown here are distributions now using those millimeter or submillimeter wavelength measurements that I was just describing on surveys of several star-forming regions. So Taurus and Ophiuchus are among the two nearest star-forming regions, and that's why they get a lot of attention. And the sensitivity then a fixed sensitivity will translate into the lowest possible disk mass for those regions. And then also the Orion region, which is the nearest of the larger giant molecular clouds. So what you see here is a distribution then of the disk masses. Now in this case, that dust emission that's been measured has been translated into a full disk mass, assuming that there's about 100 times the mass in gas compared to the dust that's actually measured. And so what you see is that there's an intriguing trend that you see quite a wide range of disk masses. So it's not that everything starts off at a common starting point. And so even for objects of the same age, this is quite you can see a span, the scale. Each of these ticks is an order of magnitude, so there's quite a substantial range. Now, the fact that there's a limited sensitivity in the previously completed and out in the literature large-scale surveys complicates the comparison. So if you want to compare Orion to these nearer regions, then quite a bit of the nearer regions, all of these lower mass disks are no longer detectable at Orion, so there have to be a lot of trimming, and so that complicates things. And so if you take a look at, you might think, well, given that we have these nice 3 examples and they have very different stellar densities, Taurus is very low stellar density region compared to, you can see all the stars packed into Orion, and it's not simply a fact that it's further away, it's genuinely much higher stellar density. So if we take those existing measurements, it's quite hard to understand if there really is a distinction between the regions. There are fairly large uncertainties, so I would say this is an area where, potentially there's a lower diffraction in the higher stellar density environments, but I think it's upcoming results that will be more definitive. But looking at Orion specifically, there has been a nice ALMA study where then there's sensitivity uniform across the Orion region, and the question under investigation in this study was to understand if near these really nasty O stars, if the environment within the Orion cloud closer to that intense radiation field has impacted the disks. So it's thought that more stars form in regions like Orion than Taurus, so it's really important to understand the environmental effects of this type of region. So with these colored points show the fields that were investigated with ALMA, and this gives you an example of one image. This is only on the order of 15 or 20 arc seconds, and you already see each of those little points that you're seeing is a detected disk around a young star. And so then by comparing these disk fluxes, which translate to disk masses, and comparing that on the y-axis as a function of the distance from this very intense radiation field of the most massive star, Theta 1c, what you see is this decline in disk mass for same age objects. But the closer and closer you get to this horrible environment, it's clearly having an impact on the available disk mass. And what's shown in this dashed line here is a benchmark comparison that's often used to understand, well, how do we understand if the mass that's present around this object is really sufficient to form a planetary system like our own. And so this minimum mass solar nebula benchmark value is used, which is the essentially the amount of solar composition material that would be required to form our solar system. And so you can see that further from the central O star, there are certainly objects with that capacity, whereas closer in there's a total lack of such massive disks. Okay, and so then if we saw earlier that there were certainly indications of trends in the planet population as a function of the central object mass, so then what then do we see similarly with disks around objects of different mass and at those different evolutionary stages? Well, for this we'd like to study one population, and so the population that's really been best studied is the Taurus star-forming region. So it has the advantage that it has very well-studied membership of several hundred objects. So there are about 350 known members. It's young and nearby. The density, while lower than what you might think that a typical star might form in, it's helpful for observations because it means that some of the poor angular resolution associated with single dish observations, that's still fine to separate individually the objects. So we can investigate the individual disks around each object. Now it doesn't have those really highest mass stars, and we'll see how we have to combine Taurus with other regions if we want to get a full picture of disks around more massive stars. But sticking to Taurus for the moment, what we see is that for those different evolutionary classes of class 1, class 2, and class 3, we do see examples of disks around all of those objects. The different colors here are indicating how you build up this type of measurement from different facilities. And then we can look at the frequency of finding those sort of disks around, concentrating for the moment on the lower mass objects. Excuse me, maybe I should violate the drinking rule. So if we look at the targets that are that will become M stars or brown dwarfs, then what we see is that for the class 1 objects, 100% of them have this disk emission, or this excess emission above the photosphere. As we go to class 2, still a very high rate, 3/4 of these objects have some type of disk material around them, whereas by the class 3 stage, very, very few. And so that's important that even in a region where the objects are thought to, at the class 2 and 3 stage, have comparable ages, they don't necessarily all have disks. Okay, and then what we can do is combine, that was from Herschel data, that was focusing on, with Herschel's increased sensitivity, the lower mass members, and then we can combine that with existing Spitzer surveys that were very sensitive to the more solar type stars, and build up for a star forming region a full distribution of the flux at 70 microns as a function of the spectral type across that whole spectral range of Taurus. And so you see a decline with the spectral type, but then if you look at it instead of an absolute flux level as an excess over the photosphere, then what you see is a fairly flat distribution with a lot of scatter. And so it appears that the disk excess is a fairly constant frequency, or a fairly constant percentage of the photosphere flux, but then at any given mass, there's a considerable scatter. Okay, so then what happens if we go out to longer wavelengths? So at the far IR, we can get an indication of whether there's disk material, but it's harder to say what the disk mass is. So if we go out to longer wavelengths with ALMA, focusing on the lowest mass members, and with submillimeter single dish facilities like CSO and JCMT for the higher mass members, what we can do is look at the disk mass then as a function. So the disk mass is here as a function of the object mass. And so this plot on the left is showing before some of our ALMA data on the lowest mass Taurus members. The green points are Taurus, and then there's a nearby OB association, SCO-SEN, which had a number of surveys conducted as well, and so those are older objects, and they're shown in purple. And so what's only shown here are detections, just to get a sense of the upper envelope. Once all the upper limits get included, the plot gets far busier. So what you can see here is that there's a systematic decline in disk mass over this more like 1 to 2 million year age of Taurus to the something more like 5 to 10 million year age of upper SCO. And then what's shown on the right is the addition when we bring in now new ALMA observations, and we're able to probe this lowest mass range where there are many M stars, because it's worth considering that in Taurus, about half of the objects are going to be M stars. So it's not an obscure little star population. This is really the bulk of the population. Okay, and what we see is that, again, as you would expect with scatter and flux, you're seeing a significant scatter in the disk mass, even for a given central object mass, but generally a fraction of the central object mass. Okay, and so now because Taurus is lacking in the more massive stars, to fill out this mass distribution for disks, we have to go to other regions to investigate more like A stars, B stars, O stars, and so that's what's been done here in this diagram. It's again the disk mass as a function of object mass, but the Taurus and Ophiuchus surveys that were available a couple years ago have been combined with searches individually of Herbig AEB stars that are nearby, and have their disk fluxes converted with their known distances into masses. And so you see a continuation of this trend of higher disk mass with higher central object mass until you get to the O stars, where then there were simply no detections at all. So those disks may simply live too short for the lifetime to be caught in the observation, or there's some different process that's really very hostile to forming disks at all. I mean, you could view it as being the absolutely closest you could get to an O-star environment. Okay. Oh, and then again, this is an area where there are quite a number of ALMA programs approved in the queue that will hopefully fill in to a much greater extent these low mass objects. Okay, so then another possible area that we can investigate with these millimeter and submillimeter observations is understanding the initial steps of the planet formation process and understanding has there been grain growth within the disks. And we can do that by investigating the slope of the emission. And so that's been done here. What's shown on the example on the right is a combination of torus and Ophiuchus data that's plotted not as a function of spectral type, but as a function of the object flux, whether or not the slope is such that you would infer that grain growth has occurred. Because there are theoretical models that suggest that it may be harder for this growth process to proceed around the lowest disks, around the lowest mass object. So it's of considerable interest to understand, is there a similar level of grain growth or not in these brown dwarfs, which are the most extreme case of that process. So what was found on these initial two disks, these red points, those are two brown dwarfs in Ophiuchus. It was noted that that slope is really comparable to slopes that have been measured for higher mass stars. And so there's no clear indication yet, anyway, from these brightest two objects. And then what's shown here is now as a function of spectral type, objects within torus that similarly have this slope measured. And again, even these lowest mass stars and brown dwarfs, there's already an indication of this process proceeding. And there are, again, larger scale surveys. The existing data is limited to the absolute brightest examples of any given class. And so upcoming will be larger scale surveys for this type of information. Okay, and then if we look at now the disk mass as a function, again the disk mass here, as a function of the evolutionary class, we can understand whether the disk mass is declining. And this is a combination of data from torus and Ophiuchus. And what you see is that the class 1 objects certainly have more emission, a larger amount of mass. And then the interesting distinction here is between class 2 objects and transition disks, which are objects where the spectral energy distribution has a dip at certain wavelength ranges, and that's thought to indicate a lack of material. And so that seems consistent with these measurements of lower disk mass associated with those spectral energy distribution shapes where there's an indication of flux being carved out, and so there's less material there. Okay, so for binary systems, another common type of star, I thought I'd give just a tiny background here where, how many of you are twins? 1, 2, 3. Okay, so 3 out of, I don't know, 100 or so. So only a very small percentage, but it's very different when you go to stars. So people formation produces binaries on a very low frequency, but a star formation, it's completely the opposite. So if we look at the nearest stars, something is certainly on the order of half of stars. And then as we go to some of the lower density nearby star forming regions, even a higher percentage are in multiple systems. So it's quite important then to understand, and we know that there are planets in these types of systems, so what are the disk properties? Okay, so this is just a real quick overview of the binary properties around objects of different masses. So what's shown here is the fraction of stars that are in binary systems as a function of the primary mass, and you see for the more massive stars a higher binary frequency, and then what's shown over here is the histogram of the separations over here, and so you see the peak of this separation, so how widely, what the distance is between the two stars is growing as you go to more massive stars. And these scales up here are interesting because these are in the few AU to hundreds of AU, the scale associated with disks. Okay, so it's very interesting that there would be another star within the region of something on the order of the solar system. So what's shown here is an investigation that was done to target each component of binary systems and to understand the flux of that pair as a function of those binary separations. And what's shown as black over here are the comparison population from single stars. And so what you see is that for those widest pairs, their distribution is really quite similar to the singles. And then as you go to closer and closer systems, the flux is, and associated mass is considerably lower, except for these closest systems, those circumbinary, these would be circumbinary rings. So where the pair is so close that the dust must must be extended around the two stars. And so these might well be the origins then of some of those very interesting Kepler systems of circumbinary planets. Okay, and then looking at the individual disk, is the primary or the secondary a favored site for planet formation? Well, what's shown here is the flux of the secondary compared to the flux of the primary. And so what you see are so gray points mean that the secondary wasn't actually detected, and black is where both are detected. And this was an early study that was indicating that the primary was almost always the more massive disk, and quite often the secondary was not detected. However, in a more recent study with greater sensitivity from ALMA, what's plotted here, it's a little different scale, but what you see are the fluxes taking into account the different mass of the primary or secondary. With ALMA, most disks were detected, both around both component, and if you think about the mass of the object, then the distribution of disk masses is similar. Okay, and then just a final note on some of the comparison of these. With ALMA, it's possible to spatially resolve the disks around each component. And so what's shown up here is an example where two disks are detected, and this is a velocity map, and so the cutting across the velocities is tracing the axis of the disk. And so you see that the two disks are misaligned. And then there are examples as well where you can go to extremely low mass companions. This is a case where a young object in Taurus has a planetary mass companion, FW Tau C. And surprisingly, that's the object with the disk, not the host star. And then again, here's another example where there's a young, very low mass companion, possibly in the planet regime, that has a misaligned disk with the central object star, which might be giving us an indication of how those objects formed. Okay, and then just a quick note that something that I think is upcoming for ALMA will be many more investigations on spatially resolved structures, and then I'll just put up a summary and ask for questions you might have. So for the disk age, okay, yes, exactly. Sorry. So the question was trying to understand what sort of initial conditions do you choose when you're setting up a model to fit the spectral energy distribution here. Sorry, I'm trying to get to the slide here. So how do you choose these parameters, and then how do those values change with time? And a question of how do you understand what the age of these objects are to begin with. So for the age of the targets to begin with, that's actually their whole field, their whole conferences on understanding stellar ages. So many of these targets have the benefit of being in regions or in clusters, and so in aggregate, the full stellar population can be fit with evolutionary models, and that's a common way to infer the age. And then what's interesting is that there's a distribution of the disk properties even at a given age. And so each disk would be fit individually with these parameters. It's not when you fit the spectral energy distribution here, it's not so much evolving it in time as a snapshot in time. But we can use different regions to understand that evolution. Oh, yeah, okay, yes. So for the distribution of the disk, okay, so the question is, why are there... Yes, in Orion, or for Fucus. Okay, yes, so what's shown here, this is some of those the question is about why is there a lack of lowest mass disks in Ophiuchus? And so this is one of those aspects where the observational biases impinge, and that's what I didn't have time to give you the details of, but it's good that you ask. The light-shaded bins are meant to be bins of common sensitivity, and you see that the Ophiuchus survey is only really sensitive to its last light-shaded bin. And so that's where this deficit can't be really probed with this data, and that's where the more sensitive ALMA data that will go, well over here, that will then make it possible to study the lowest mass disk comparison. Yeah. So they don't necessarily always. Oh yeah, sorry. So the question was, is there a requirement of an assumption that the disk is flat and circular in inferring the properties when modeling the disks. So it depends in part on the type of data you have. So for these spectral energy distributions, there's no way to understand really about asymmetries in like radial direction, but we can learn something about whether the disk is flat or flared. But then as we go to these really more recent data sets, then we can get information about structure. And so with the most recent maps of both very early stage HL tau disk, then we're seeing asymmetry, and these are examples of transition disks with clumps. So then we can move forward on understanding the asymmetries with spatially resolved maps.